Other mic? Sir, this is what, sir?
No. That. No, I'm saying
Yes, there is one more.
I think it's there.
But other people,
Ashok.
where all are those trucks, huh? They were all there, no? Right now.
Yeah, I saw them. They come.
In 1 week. That's 16. Both 17. Possibly. The other dates are this 80%. I can tell you, when does it have expansion? September 1st.
No one was outside waiting or having tea. It's fine. We'll get some.
That is a pointer.
Yeah.
Hello and welcome to this week's string seminar. So after a set of lectures today, Jnan Maharana will tell us about production of KK states in large radius compactification scenario.
So, thank you very much for having me here. If I did not make a mess in last 2 lectures, so the mess will be complete today. Okay, so first of all, I would like to thank ICTS for having me here. I don't know after how many years, long time. But also I want to share sort of my thoughts little bit in the sense that probably in this hall at least I am the oldest person, and in 1984 when this paper on anomaly cancellation came, I think it was kind of a revolutionary thing, and then the heterotic string paper came. I was at CERN during 85, 86, and everybody was so excited And I think in October they have a meeting, everybody goes to the board and says for 5 minutes what he's doing. So then I later counted that out of 120 people, 110 were doing string theory. So you can imagine. And but then the young postdocs, they always will be talking, and they will be talking to each other. And in the coffee room, some people will say, well, we are there, we are almost there, we are around the corner. And then some people will say, see, heterotic plus scala bia. Okay. So, I mean, basically it is, but theory of everything has not been coined at that time. But some people will say, it's just question of time that we'll calculate muon mass. Because there is only one dimensional parameter in string theory. So this is a fundamental theory, it should be. But this is not to make you pessimistic. But the point is, if you see decade by decade, not year by year, from 1984 onwards, you will find at every decade there has been really great progress in understanding string theory. Okay, so it is not that without offending other fields that there are these very accurate programs to calculate corrections. No, and then some of the architects of this progress, okay, really fundamental progress step by step are in this institute. But still I want to tell the young people, one has not been able to calculate muon mass. So therefore there is some problem left, okay, to calculate the muon mass. But somehow last few years, there's only a few more years left, so I started thinking that whether one can sort of try to see if something can be done to check that whether there is any experimental evidence for string theory. So not that I will provide you an evidence, but I think it is worth checking, and also one is far from the mainstream. So therefore, I actually invested some time last few years. So this just summarizes, okay? So first, we know this has been tested very well experimentally, really with great degree of accuracy. Second, there are many reasons to believe that this is not kind of the end, because that this theory is incomplete. Example, you cannot compute Higgs coupling, okay? Or say Higgs mass. There are many problems. So actually experimentalists also believe that there are reasons that this is not complete, okay? And then there are guts to unify three interactions. And one of the testing points was proton decay. And so far, actually, there is no experimental evidence for proton decay, but there is a limit on the lifetime. So, but as I told you, the superstring theory actually probably, it's not outrageous to say, the only theory which actually holds the prospect of unifying all four fundamental forces, in the sense someday we will actually test it against experiments. So, but we live in 4 dimensions, and consistent theories like heterotic string theory actually is defined in 10 dimensions. So the proposal was right from the beginning that 6 of the extra dimensions are compactified. So nobody has come to a conclusion that which compactification works, but it is compactified. Now, therefore, those days, general idea was actually compactification scale might be in the vicinity of Planck scale or in the vicinity of Gutt scale. So then beyond the 0 modes, okay, we actually had no chance of experimentally observing those things. But I think, so where can we see this? But then I think, I don't know, 2003, or 2005, when this idea of large compactification radius came, this ADD and AADD, okay? And so crudely speaking, that actually the scale could be in the TeV scale, okay? And at that time I got interested, but then I started reading some papers and found that they're all models and mostly tree level kind of thing. So I lost interest, okay? And then I have not checked, you can check. There are probably a few thousand papers on this subject, okay? And then, as I told you, last 5 years, so I have been interested in these things, but from sort of as an outsider, and I talk to experimentalists from time to time, because there are two groups, one in Atlas, another in CMS, who are actually looking for these exotic phenomena in physics. So I understand from the conversations that the scale could be 2 TeV to 6 TeV, because they have to put some input from models, okay? So, so this is a small comment that sometimes I'll talk about small, weak and strong bounds. Suppose you have a power of log with same set of assumptions. If you have a lower power of log, same assumptions, then it is a stronger bound. If it is actually higher power of log, so I'll call it weaker bound, okay? So this is just a question of nomenclature. Okay. So general outline is, I'll consider inelastic scattering amplitude in a theory with S1 compactification. So from phenomenological point of view, there are some questions about S1 compactification. But if you compactify from higher dimensional theory, that whatever I say is not going to pose any problem. It is not S1 specific. So then I'll talk about production of these particles in large radius compactification proposal. So the space-time is 4-dimensional and there is S1. And then I'll spend quite a bit of time about studying the analyticity properties of inelastic scattering amplitudes, this production amplitude, and then suppose the theory decompactifies, then what happens, okay? This is the idea, because I sort of think, maybe I'm not right, but if we want to see this in near future, any evidence, so maybe they will be produced in LHC. So in fact, last time I was in correspondence with some these people in CMS, exotic physics group. So they have shown some interest to learn a little bit more about what I am doing. Okay. This is what I told the other day. Just to summarize very quickly, that what we know, that for 4-dimensional field theory, the Froissart bound is this. Total cross section is bounded by log a square, okay? And this prefactor is determined from basic axioms of quantum field theory. I'll go through very quickly these things. And then what goes into deriving this is the analyticity of the scattering amplitude FST in the cut S-plane, and is polynomial bounded, where n is integer. Okay. So this has been proved rather rigorously, and it satisfies dispersion relation in T inside the Lehmann-Martin ellipse. That also I talked about, and crossing symmetry also proved. That means particle, antiparticle cross amplitudes are analytic continuation of each other. And then the convergence of the partial wave amplitude inside Lehmann-Martin ellipse, which is the complex cos theta plane, and unitarity, of course. And so for partial wave amplitudes, this inequality is satisfied. Okay. This is all known. Okay. So this is that the scattering amplitude is boundary value of an analytic function in the complex S-plane. So complex U plane, and there is a cut starting from the threshold for equal mass case is 4m square. That's the right hand cut, and then there is a left hand cut from U threshold. And okay, so this is the partial wave amplitude. So there are problems I discussed. I need not go into all this, but basically what is known today is that the scattering, the partial wave amplitude converges inside this bigger domain called Lehmann-Martin. This is all known. Okay. So, there is actually compelling theoretical evidences and also experimental people think that maybe D is not equal to 4. There is some physics beyond D equal to 4. Okay. And so I'll consider this S1 compactification. And already I studied, okay, the analyticity property for this compactification in a different context. But I will not talk about all that. So I will talk about the inelastic processes, particularly in LHC if proton scatter into production of these excited states, the Kaluza-KLein states. So this is not necessarily a string theory, okay, but this could come from some string effective action, but just a theory which lives in 5 dimensions. Then I will, you have to go beyond all these axioms. So I will sort of choose what is known as, I thought it is simplest, universal extra dimension hypothesis. Okay, this problem has its own. Okay, and which of these models don't have problems? Actually, in fact, there is no such model which has no problems. Okay, and so if you are interested, you can search. There are 13 lectures review on large radius compactification hypothesis with various models and various sort of scenario. But this universal extra dimension hypothesis sort of says that we have standard model fields or particles in D equal to 4, then you promote it to D hat, which is D plus n dimensional extra dimensions which are compactified eventually. One. Second, the constituents of D is equal to 4 standard model are 0 modes of this higher dimensional theory. So as you come to D equal to 4, there will be KK states, okay, the Kaluza-KLein states. If the radius is large, these states can be produced in LHC, okay. Yes. Yes.
Since you started the discussion of experiment, can one really ever falsify or check the Frost bound? Let's say we found the bound was being violated. Couldn't it be that actually the bound will be obeyed at higher energies? Can we, let's say we found...
No, you mean higher energies, it will... Oh yeah, for example, if you are at low enough energy, so near some threshold production of some particles, so the cross-section doesn't obey Frost bound, okay? But these are all asymptotic bounds.
I understand. So is there any experimental significance of this bound? Because I could always find that I'm violating things, but maybe that only tells me that I haven't reached the asymptotic.
Oh yeah, that is one simplest explanation. Yes, that you have not reached asymptotic. And in fact, yesterday I just commented on this. There is a paper, I think, I don't know, 10 years ago from Brazil. They claim that it violated Frost bound. Okay, it was published in Brazilian journal. But the editor of the journal, having published that, they actually referred this work to a person called Black and his collaborators who has been fitting total cross-section data all his, this group, all his life. And they took same set of data and then they took same parameterization and carefully analyzed, and they found no violation of Frost bound. Of course, what you say is right, but whenever you say violation of Frost bound, you can always claim that we have not reached the asymptotic. Okay.
Yeah, and string theory probably will never reach asymptotics because there are infinite number of resolutions.
Yes, you are right. So in string theory, besides Frost bound, there are also other problems to prove Frost bound. So
you're saying it will never be okay. It's not even okay.
Yeah,
threshold.
Exactly.
But there is a cone, right, in which you can.
You have to go complex outside. The
Outside.
Yes, but
Not, of course, on the real axis.
yes, but still, see, there are already, because of these massless states in the string theory. So I'm not saying that this in the context of string theory, because it's an extended object. So it is that all those axioms will be obeyed. Why should they be obeyed, right? But so if string theory really, if you find independent evidence for string theory, okay, whatever so therefore, if this bound is violated, it is nothing sacred is violated, okay?
Sorry, I didn't understand. Is one of the assumptions that the spectrum is bounded above? The masses are bounded above?
Oh, no. But what is there is a mass gap, okay?
That is true, but suppose you have infinite number of.
Of course, that is another problem. I'll have no time to talk about that because there is a paper, very old paper of Andre Marta, is that if actually a new threshold opens up, okay, and you need not see that opening up. Below that threshold, when you try to write dispersion relation will be modified, okay? He doesn't say violated. Now imagine that in this case, there are every sort of energy intervals, new thresholds are opening up, right? So to write a dispersion relation for such a theory, I do not know how to write. So if dispersion relation today, as far as my knowledge is concerned, if that dispersion relation is violated, I will not be, very upset.
But in QCD, there are an infinite number of thresholds.
Yes. But that is a good point. No. I'm telling why it is a good point. That
But in UCD, you can say at high energy, you can use quad description, right? Then you don't use example.
No, but this is supposed to be for, say, proton-proton scattering or something, proton-antiproton.
No, but you raised a very good point, because I think it is 2018 I was at CERN, and Andre Marta came to me and he was very upset because physical review referee had raised that we know the fundamental theory of strong interaction is actually QCD. So when you are deriving these bounds on proton-proton scattering, it has no relevance. Okay, well, it was not exactly this sentence, but it was very strong. So he was very upset, and he told me that I know who is the referee. He is all this. I said, but Andre, the basis on which you derive these results actually assumes there are actually asymptotic states that you can construct in and out state. Since QCD is a confining theory, so even in LHC experiment, you prepare two protons, and in the detector itself, you only detect hadrons, okay? You reconstruct back saying jets. So he was a little bit relieved. Then he said, but what do we do?
But there are asymptotic states in QCD, they're not quarks.
No, that is what I'm saying. So what you observe are actually hadrons, okay? So that is what I'm saying. So because the referee had raised that, why are you calculating this, okay? So then second thing I said, but then there are bound states, you see. There is this problem of bound states. So.
But you don't know what is a bound state, what is not a bound state. There will be another description in which there are fundamental states.
Yes. No, but what I'm saying, that naively, okay. So there is this construction of Hart, Nishijima, and Zimmerman, which actually gives a construction how to treat bound state in LSZ. Okay, I don't know if I have heard of this, but yeah. So I said you actually.
Any operator which has a one amplitude, one particle state.
Yes.
So you should give me like the proton and stick product of three quarks, and that's it. That will give me a.
So, but there is some condition when something will be bound state. I've said it long ago.
If there's a pole, you have to look at the single particle pole.
So yeah.
Function.
Yes, but then there is a condition under what circumstances, okay? Starting from some elementary objects, if you have a composite object, what is the condition? There is a HNZ condition, okay? I don't remember that.
So, but this Froissart bound, I thought is true for asymptotically even QCD or proton scattering, provided you go away from the real axis.
Yeah, what is that? How do you, so you say you compute in QCD, and where do you have to go?
You have to be off the real axis, because on the real axis there'll be thresholds. So
real S, complex T and U.
No, complex S plus I.
Oh, I see. So you do S plus I.
Something, yeah. Some cone I think you need, but it can be probably, yeah, it can be probably a very
I see.
infinitely
Because you
narrow
have to be the analytic. Oh, so you go above
Yeah. The problem is that you are asking, putting it on a cross section, not on scattering amplitude, right? Amplitude sort can understand that you can go off. But cross section is a little.
Yeah.
But amplitude, there is also a similar.
Amplitude you define, as I said, that with this I epsilon prescription that you approach from above.
I'm confused actually. Even if you put it from above as you approach the point, the start of some branch cut, you can.
Then you will blow up. It will be unbounded.
How will this log of S work? You have to not be anywhere.
You have to not be. You have to be in a thing, a cone which avoids the whole thing. I think that's how I think at least, like even managing amplitude when you talk of its asymptotic behavior.
Yeah, you have to do little bit.
You have to talk about you get to the
little bit. You have to just go off the real.
But when you are talking about the cross section, right?
Yeah.
You have a amplitude times its conjugate. So
yeah.
Above the real axis means its conjugate will be from below the real axis.
Yeah, because as you approach this reflectivity property.
So it's not that you are taking some analytic function of S and then.
No, say FF star.
I can understand this.
FF star.
FF star, yeah. So FF star will analytically continue.
Yeah, but I mean, forget about the experiments, but theoretically, I mean, there is a Froissart bound for the amplitude also, right?
No. The bound is for polynomial boundedness is for mod of FST bounded by polynomial. Okay, but there's a little bit more to it because there is you have the cut on the S channel, then you have a cut on the U. Okay, so now if a little bit off this cut, other side that, now inside this wedge, if on this line and the other line, it is polynomially bounded, okay, then it is polynomially bounded on the entire plane, okay. This is this Jnan Maharana-On bound, okay. This is based on some complex variable theorem that you have a line like this. It is not necessarily like this. It could be wedge, but it is bounded here, then it is bounded in the entire domain. Okay. So, modulo. All right. So then this is some properties of this model. Okay. So you see, I'll focus on this, that a pair of KK states are produced in PP collision. So you see, since and these KK states have the KK charge, okay, they have to equal or opposite charge. So initial quantum numbers, the additive quantum numbers must add up to final states. So this must have a baryon number, so on, charge, everything that you want. All right.
So this model, so it's not that just gravity is in expanded.
No. This is just flat space.
All of it is.
Just one single field theory in 5-dimensional flat space, and you compactify on S1, you are also in flat space.
So regarding this PPTC and so on, so this will basically destroy the, because you're putting a lot of colored particles.
Well, yeah, you will put color particles as we discussed. Okay, so color particles will be there, but when you come asymptotically free. Okay, so there is no. Although, yeah, if you actually did the full theory.
So there is no brain.
Huh?
In this, there is no brain.
There is no brain.
There's no what?
Brain.
There's no brain. So, I thought, sorry, this is not a computation you do in string theory.
No, I told you in the beginning that all these models, not necessarily they follow from string theory, okay? There are various kind of variants of that, okay? So the one I am taking is the simplest.
It's just 5-dimensional effective field here.
Yes,
5-dimensional standard,
and massive.
not standard model. That is
No, see, one species, okay, one species of a scalar field which lives in 5 dimensions, there is no gravity there, no gravity here, and you come down to.
So only one species lives in 5 dimensions. Rest.
No, I actually don't talk about rest. In principle, what I follow for S1 compactification, you can do all for the rest, okay? But you will see this already, this single particle is already quite a mess, okay?
No, I think what Loga is saying that if you try to make, for example, the gauge theory also in 5 dimensions,
Yes.
then it will not be asymptotically free anymore, right? Because
Yeah, so, yeah, but I think these people actually engineer something, those who
you
do.
have a brain, right? Gauge theory
The
problem lives on the brain and
probably, yeah.
gravity lives in the ball.
So-
So you have a scalar field living in the ball, but as long as
Yeah.
that's not part of the standard model.
So,
it's a random syndrome, right?
No, I think ADD didn't have the warping. Random syndrome has the warping.
no, they didn't have. But there are all sorts of variations. Those days, I remember. And you sort of pick up your favorite configuration, and effectively, essentially, you write kind of a Venetian or Virasoro amplitude, and then you see what happens if there is extra dimension. Okay, like some states disappearing into the extra dimensions and missing energy and so on. Okay.
So the point is that you have a KK double for every part. Standard model.
Yes, yes. When you come down, if you have all the standard model fields there, okay, when you compactify, okay, you will have KK modes for each one of them.
So,
Yes.
And the KK tower, the lightest KK tower would be like, I mean, there'll be the same mass hierarchy.
Well, you see, the lightest one, the mass will be inversely proportional to radius of compactification, crudely speaking, right?
Yeah, but there's already some hierarchy of masses. Let's say the neutron is very light. Right?
Oh, yes.
So let's say like the KK is not the lightest.
Yeah, KK neutrino, if you neutrino lived in 5 dimensions, so compactified KK neutrino will also have its KK.
That's the lightest, like the KK part, or
He's taking only one field
Yeah.
in 5 dimensions,
So
so
one-
it could be even a massless scalar field.
No, I'll take massive,
Massive
yeah.
scalar. So there's only one massive scalar field in 5 dimensions, and then it's KK tower when you
everything else is living for us.
effectively.
Yeah, but you see, you could add everything and you can make a 5-dimensional or whatever dimensional effective action except gravity, and then you compactify on S1. So you will have the 0 modes of all that is standard model spectrum, and then on top of each one of them, okay, you will have.
Yeah, I was asking if all the fields live, but I think from what you're answering, only one scalar field lives in 5 dimensions, but everything else lives in 4 dimensions.
Yeah, but I'm not talking about everything else either, because for
What
this.
you're saying, Carl, is it will not matter because you'll only consider one species.
One species. And whatever complications you see for this, okay, those actually are valid for n number of fields.
Produce everything. So
Yeah.
Yeah, if you work at that level,
Yeah.
but if you're just considering it
Oh.
level production, maybe just.
One, and second, those who have done phenomenology, they actually have to make sure that when you do loop corrections where these particles circulate, then the standard model results, whatever is experimentally tested, okay, are not upset. So that puts some kind of a constraint on the theory, okay?
So I'm just trying to understand this comment that you made 2 slides ago, that you should not change the UV behavior.
I shouldn't change.
So we had, like the previous slide, there can't be one field and so can't be effective correction, should then is that equal for effective change? Oh, this is what you mean. You're saying you should not upset things like that.
Yeah. Yes. So I think if you do the phenomenology and do the perturbation theory, I don't know, means those models, I think there are many problems, okay? And so therefore, today in the market, you hardly see any paper on this large extra dimensions. Okay.
So your R will be a what? AB?
Yeah, R I'll take in the, I can't actually tell you a number, but R will be in TeV range. Because KK towers, if they are not they don't start with, let's say, 13 TeV. That is the end of the story, right? All right. So, sorry. So I want to derive bounds on this. This is for and differential cross sections.
So you get ABCD, all of them are standard.
No. You see, A, B are this is proton. This is K1, K2. Okay. You in a moment you will see the mess. Okay, already with this. So this is whatever I told last 2 days. So I will not spend time on that. But just one point, you see, standard LSZ, there is a Hilbert space. Okay. So what happens here when you compactify? So you see, these are the ones in 5-dimensional theory, the in and out states and so on. So, and this is also I did. So now you see, when I compactify on S1, so this is free field equation, okay, in 5-dimensional theory. Now, when I actually compactify, you see, there is this. So Y is periodic with radius R. Now, when you write down the free field equation, it transfers to this, okay? So, Mn square is M0 square plus N square over R square, N is equal to 0 is 0 mode. And then you see, now momentum is an additive quantum number. So now, same thing with the interacting field. So you have the source current, and this is the source current which carries the Kaluza-KLein charge. Now you see, for 0 mode, you can actually build the Hilbert space, the Fock space, and the positive. And then this creation operator creates a state which has KK quantum number. Okay, and they are orthogonal because of the additive charge quantum number. So this is the orthogonality. Therefore, the original Hilbert space actually decomposes into all these states which carry KK quantum numbers or the charge. Okay, so now this is standard definition of minus time variables S and T and U, and because the KK states are equal mass, so Mandelson relation is twice M square, MA square plus MC square. All right. So now the kinematics is a little bit complicated. So this is the center mass momentum for the incoming particles. This is the center mass momentum for outgoing particles. And now you see cos theta is a little bit modified compared to what we did earlier. Now, this is, just to repeat, this is a state, 2 or more particle state which has quantum number of A, and similarly C, B, C, D. This is the two or more particle state which has quantum number of AB, AC, AD, BC, BD, CD. Okay, so this is useful to study analyticity property as we saw. So now the amplitude, this is the disconnected part. So this is the LSZ reduction. All right. So now after we did all the reduction, you see that this Klein-Gordon operator acting on one of the Kaluza-KLein states actually gives you the charge. Okay, the charge of this current which has charge N. And then you see when there are 2 of them, to conserve the charge, okay, this has 1, this has minus N minus N, so this is the R product. Okay. Okay. So this is okay. Let me just make this qualifying remark that this is not strictly correct because there are terms which are delta function, derivative of delta function, and so on. But as I argued other day, that when you take the Fourier transform, they are all momenta, product of momenta, but they have to be Lorentz scalars. So they will all depend on STU, whatever it is. So the properties of the amplitude, they really don't affect very much. And then the extra terms, okay, there will be terms which will be equal time commutator of two field operators, so they will vanish by microcausality and so on. Okay, this I also did other day. These are the three distributions. So I'll just focus on this one. Okay, you see there is a theta function here. So this is the retarded function, this is the advanced one, and this is the so-called causal one. So end of all this, as I said yesterday, that this actually reduces to giving you a mass gap. You see, when you take this causal commutator, insert complete set of states. So this is actually momentum conservation. Okay, Pn, because they're all physical on-shell states. Okay, so they must satisfy this condition. That is why this happens, and then this is the mass gap condition, that there have to be minimum mass in the theory, okay, and with positive energy. This is sort of known stuff. Okay. So this is, and then using all these things as we discussed other day, so you derive existence of small Lehmann ellipse, large Lehmann ellipse, and so on. But this we did for elastic case. Okay. So now for inelastic, you see the two momenta are different. So center mass momenta, this is the one for incoming particles, this is for the outgoing particles, and so on. So T actually is bounded by this. In this range, this T is sort of defined properly to write dispersion relation. Okay. Similarly, this is the so-called semi-major axis of this ellipse, and you can see this is greater than 1. Now, this is a little bit of mess, as you can see. So, yeah, go ahead. No, ask.
What are we trying to prove?
No, you see, to prove the analyticity of the scattering amplitude for fixed T, okay, so what is the value of domain of T in which you can actually define the scattering amplitude, okay? So, see, in cos theta language, cos theta is +1 -1, okay? Now, if actually you confine yourself to cos theta +1 -1, this interval, now if you want to write a fixed T dispersion relation, then from the, okay, let me just write down somewhere. No, just this will actually, no. So let me just write down this. T is equal to equal mass case. The problem is a little bit complicated. So you see, if you want to hold T fixed, okay, and as you go to threshold, you will go K square going to 0. So if you want to threshold, you see, S is equal to, okay, K square, P1 plus P2 whole square. So that is equal to P10 plus P20, okay, whole square minus P1 plus P2 whole square. So as you go towards S threshold, so K square goes to 0, center mass momentum. Now what happens, you see, because of this relation, if you want to hold T fixed, okay, and let K square go towards 0, the cos theta must go out of physical ±1. Okay, so there is this very old problem, and therefore, if you want to write a fixed T dispersion relation, so this scattering amplitude in cos theta has to be analytic in a slightly larger domain.
Can I just ask, you are talking now for Kaluza-KLein particles.
Yeah.
Suppose these are just some two ordinary particles.
Yes. Right.
Why can't we think of the Kaluza-KLein particles as just some ordinary?
No, all this is actually, whatever I have done, it is just kinematics for unequal mass scattering. That means A plus B.
So these KK particles could be some arbitrary.
Yeah, it could be have mass which is different from initial mass.
So then this analysis is different from what you described earlier because they are considering unequal mass.
Unequal mass. So that is what the cause of the complications. Since you were there, so all the simplifications that were there, they will all be complicated. One. Second, because
you are trying to derive the analog of the Lemon ellipse.
Yes, I actually derived that. So that is one. Second, you see, because we are considering inelastic scattering, so there is no optical theorem here, right? So therefore, the partial wave unitarity, which is valid for elastic scattering, actually no longer, and you remember that actually it plays a role, okay, eventually.
When we read the first, when you mentioned the first hour, there was no assumption of full masses, right? Because
yes, but you see, as long as you see, you start with elastic processes, okay. One, second, unequal mass doesn't matter, but elastic. A B, okay, going to A mass is different from B, going to A B. Then you see, you can use optical theorem. That means imaginary part of the forward scattering amplitude for AB going to AB is related to total cross section. Okay, but if AB goes to CD, okay, another thing is, you see, the partial amplitude for elastic processes is actually mod FL square is bounded by imaginary part of FL, which is bounded by 1. But if you don't have elastic processes, it is not obvious that, of course, the optical theorem doesn't hold good. Then this partial of unitarity also is not valid. And partial of unitarity actually plays an important role in the derivation of Frost bound, because in the sum, you saturate the partial of unitarity. Imaginary part of FL is set equal to 1, okay, in that sum. So it becomes a very simple AP, okay. But here, you see, so you have to go through this little bit of rigmarole, okay, to even, and then consequently, as I said, that if you want to derive this Lemon ellipse, because of all these complications, okay, so it becomes more involved.
so what is LLE and SLE?
Well, one is small Lemon ellipse.
So large lemon ellipse is
Small Lemon ellipse is not good enough, okay, for writing dispersion relation. The large Lemon ellipse inside which the scattering amplitude has good behavior, means desired behavior. Okay. So you can see the mesh, and you see this is what appears. They introduce these mass parameters, okay. So this is all appears there. Okay. Now, so well, this also I talked, but basically large Lemon analysis is not enough. So because in the asymptotic S value it shrinks to real line, but then you have to do this so-called Martha's theorem. That is also. Well, but you see, this is what happens. See, in elastic scattering, A plus B going to CD, okay? And for elastic, this is the relation. But what you can do, right? The AB total cross section elastic plus all multi-particle cross sections, okay? Therefore, since each term is positive, the imaginary part of AB going to AB, okay, is actually greater than the imaginary part of the amplitude. Therefore, now instead of the old bound, what you have, mod of the partial wave amplitude is bounded by square root of elastic scattering amplitude. Okay. So it's not a big deal, but you see, you have to use this. But this has, very small effects, but eventually all these small effects add up. Okay. So you see, now we could not, okay. So this amplitude, okay, is bounded like this for large L, but now the inelastic amplitude, you see, this is the inelastic partial wave amplitude, so you all did all these things, and this is bounded this way, okay? It's a lot of donkey work. Now, you see, I'll just say a few words on this. Now, for inelastic processes, you have to be a little bit careful. The threshold is pp going to pp, 4mp square, right? But the threshold, the physical threshold for pp going to k1 plus k2 is above that. So there is a region, okay, S threshold is this. And then S threshold is greater than physical value. And third region is there, okay? So which actually in words, okay, when you work out, you have to determine in words that could, in principle, there could be a region where the this momentum becomes imaginary or complex. So that is the region where you cannot have Lehmann ellipse, okay? Therefore, for that region, you cannot write dispersion relation. So these are the associated. So there are these three domains, as I said. Okay, so where it is analytic, okay, so this is the Lehmann ellipse. And this, the so-called Lehmann-Martin ellipse is a little bit different or bigger. So in this region, from critical value to infinity, it is the Martin ellipse, okay, for inelastic processes. And third domain is when it is between physical, S physical and S prime critical, and this is the ellipse. Now, you see, this is the domain where actually your scattering, your center mass momentum could be actually complex or imaginary. There you cannot write the Lehmann ellipse if you go through the all the rigmarole, okay? So, and then for unequal mass scattering, you see, this minimum momentum transfer square is not zero. So this all these complications is there. And then also Tm, I have the expression later on, that is also has complicated. So, okay, you see, this is the comment. Must check that the center mass momenta for direct channel and those for the cross channel process do not become complex. If complex, there will be gap in S where we cannot write dispersion relation. Same argument holds for the cross channel, the U channel. And so we must check this. Okay. Because this involves a lot of square roots in the expression. Okay. So you see, good old days, in the days of the dispersion relation, you could put numbers. Example is, let us say, PP going to delta delta, right? So you have a proton mass which is 930 MeV, delta mass is 1200 something, 30. So you put everything, you extract numbers. Here, I cannot extract numbers. Okay.
I'm confused about what in any case these bounds will tell us about anything experimental in terms of.
Yes.
Because they have something which have to do with continuing off the physical scattering aspect.
Yes.
So how would they? So I'm confused about what we are trying to do. Let's say we because so in terms of something we would measure at the NHC.
Yes.
How will the bound tell us? Give us a bound or anything? How will it tell us anything about what we actually measure?
Oh, yes, because you see, when actually you let us say differential cross section. So you see, this domain includes physical T value to the maximum allowed T value for analyticity. But that ellipse includes actually physical cos theta. But yes.
I thought as we were discussing, these bounds cannot be valid in the real axis because you might just have some particle sitting there.
Oh yeah, in case, but that is right. Suppose between proton, okay, and KK particle, Suppose there is a resonance, okay, hypothetically. Then whatever I am saying will not strictly speaking be valid, because if I knew, I have to take into account the existence of the new threshold, okay. So whatever I say, okay, so that has to be modified.
Yeah, maybe the point is the bound is violated, then you know there is some threshold. So some new physics has to be there, right?
Yes, but you are right. In fact, on this issue also,
This are not, I'm confused about. First of all, I don't know what it means for the bound to be violated because we'll never be in the asymptotic region for S.
no, but you see, when you write,
But the point is, suppose you don't know whether KK particles exist or not, right?
Suppose we
You're just trying to check the Frost bound.
Yes.
And suppose you found that some part of Frost bound is violated.
I don't know what does that mean. Let's say I computed S equal to 100 TeV. I found that it's from 80 to 100 TeV, it's growing in some way.
Yeah.
Maybe that just means that I'm not in the asymptotic region.
Yeah, which means that there is something above that. Right?
That I can already check by seeing if the amplitude is agreeing with the standard model amplitude or not. So if it's disagreeing, then I already know.
Yeah.
yeah, no, but you see, the point is this, that if there are actually a threshold, okay, before even if you, actually there's an email from Jnan Maharana, he wrote some paper, good old days. But you see, suppose there is actually, before the threshold, okay, you will find when you write the dispersion relation, there is some deviation, okay, let me say not violation, deviation for what you would have expected. So before even you crossed the threshold, because you see it is some, let us say S0 to S prime, okay, S prime to let's say infinity, but in between there is one. So when you write the dispersion relation, this indirectly this dispersion relation will know that something is happening, right?
No, I've not understood. It seems that there's two ways we can check for new physics. Let's say we compute a scattering amplitude. You can see if it matches standard model or not, or we compute some cross section.
Yeah.
Are we saying that these analyses of these bounds give us some better indication?
So yeah, for example, I'll tell you total cross section, okay? PP scattering total cross section. They are measured from few GeV or before that till LHC energy with fairly good degree of accuracy. But actually, you cannot calculate total cross section from fundamental Lagrangian. Because you see, these are total cross section is mostly dominated by soft processes.
Good. So now we can't calculate. Then we come back to this problem.
And second thing is, so far, the experimental fit of PMG, okay, is from again from few GeV till LHC and whatever cosmic ray data is available to some TeV, okay. LHC TeV plus TeV that fits with is fitting by particle physics data that fits with saturation of Frost bound.
But sorry, just to understand, as we compute it, presumably it has all these peaks which correspond.
Yeah, but by particularly for PP scattering, you see, as you go to let us say 3 GeV or something, or a little bit more, it is like you can look at PP and PP bar. Unfortunately, I don't have the display. If you look at PP, okay, it sort of constant like this and then starts growing. But if you look at PP bar, so below certain energy, there will be these bumps because there are meson resonances. Then after a while, it also, and then as you go, I think as you go to ISR energy, okay, they more or less match.
Bumps will continue to be there, right? For arbitrary, because you keep producing more and more.
No, yeah, but for experimentalists, okay.
But those are probably far off the real axis.
Yeah.
They may not really.
No, but for
Yeah,
but also they will be very wide. You see.
Yes, they're very wide.
So from experimental, if you look at the data, okay, PP.
Yeah, so there'll be an envelope kind of thing which will be like log squares. That's I think what there'll be peaks or bumps or.
Yeah, but the experimentalist actually, if you look at the data, I should have actually. No, so experimentally see, I think about 3, 4 GeV or 5 GeV, say, both are smooth and then both are constant. So then after certain energy, I think center of mass energy of, let us say 20 GeV, when you hit the ISR energy, 28 GeV, they more or less become very close, okay, 5%, okay, and then you go to SPS energy, where they produce W and Z, PP bar, okay, then they are quite close, and then you go to Fermilab, okay.
But presumably as you cross the Z threshold, there will be some bounce, right?
Yeah, but you see, Z production is rather complicated, okay, and that too also is very high transverse process. So therefore, its contribution to elastic or total cross section compared, it will be, let's say, G square in weak coupling, okay.
Even I was saying there's a constant in front of this log square.
Yeah, but that is fixed
It's fixed once and for all by what?
by these axioms of LAZ.
I thought we cannot fix that constant.
No, that constant is fixed when you are going
S
to.
by S naught you can't.
Yeah,
fix.
yeah.
But the prefactor was
Yeah.
4 pi by T
When you
naught.
are going to high
The
school,
T naught is the fixed.
4m pi square.
4m pi square.
In the T channel, that's like this particle in the T
Well,
channel.
in fact, there was some pions. I mean,
No, but it is proved rather rigorously. But you see, first
Threshold in the T channel.
T channel. But you see, you have to go through all this rigmarole I was talking about to actually fix ab initio. You don't have to assume anything. You just fix this as a number. In fact, it is actually the number which is, let us say, 4mt square, where T, well, I should say 2mt is the beginning of the T channel cut. And you need that because of the Lehmann ellipse. Okay? That is the beginning of the non-analytic structure. Okay, so see, very good. I am very happy. Okay, in ICTS, people are so much interested in.
you do some PP scattering,
Hmm.
and at some point you find maybe some violation of this log square.
No, not violation even. I'll tell you, because I have been talking to these guys. You see, they have to have models. Now imagine, okay, that A plus B going to C plus D, okay, measuring this cross section, okay, so at LHC, okay. So, and there are, as I told you, 8,000 papers, there must be 150 models. So what I am giving them, that if you can at all measure the inelastic cross section, here I am telling you what is the bound. But I think I'll come to end because I have consumed my time. So, well, good. See, I'm very happy that this seminar is not totally worthless. No, but this is what I'm telling them, and that is the reason they are interested in me. Okay, and second thing is, nothing is foolproof. When I come to end, I'll say that where is, the, let us say, a catch. Catch in the sense that where there is some arbitrariness. That also I'll tell you, because I have nothing to lose. Okay. No, so, all right, let us, already 5:35, 4:35, so another 10-15 minutes. So you see, I actually tell you the domain of analyticity in a T-plane. There are so many Lehmann ellipses depending on, because the dispersion integral is over S prime, okay? So for every S, there is a Lehmann ellipse, okay? So, okay, this is, U channel is little bit better because proton going to, let us say, KK bar, I will say. So the U channel is actually elastic scattering of unequal mass, okay? So this is, you can copy from whatever is known so far. That is not a big deal. Or this, forget about this. Okay, so I'll just quote you some results, okay? So if you want to obtain this differential cross section for inelastic scattering, there is a problem here. Shashank Roy and Viren Singh many years ago actually derived bounds, okay, on differential cross sections for elastic processes where they use total cross-section in elastic cross-section as inputs in the following sense. You see, elastic cross-section is FL mod square, okay? And other one is bounded by unitary to imaginary, okay? So you can use Lagrange multiplier method, very clever trick, to actually determine, okay, the parameters that appear here, okay? And so what they found that this differential cross-section actually those days had a scaling behavior. That means you plot differential cross-section versus T, okay, with energy, and you find that all data for some scaling variable, they fall on the same curve those days. So it was very interesting. But unfortunately, for inelastic processes, this Viren Singh, Shashank Roy technique doesn't work. And still I'll just use this property, okay, the polynomial boundedness. Then I use this inequality I had derived using kind of unitary. So you see, still you will say, oh, what is the big deal? What did you do? Total inelastic cross section is bounded by log A square. It's a very weak bound, okay, in my language, but still it is a bound, okay. So it's a weak bound, but still it is a bound. As far as I know, okay, for such processes, it's not known. So as I said here, T0 is the threshold for T-channel processes, okay. Well, I don't know the masses.
The threshold is still pi, right? Because
No,
you believe
no.
K to be higher than the
Yeah, but you see T-channel.
yeah. T-channel. That's where you have
K0 bar, okay, K bar, okay. So this channel carries a KK quantum number.
But you are talking about, okay, total, not total cross section.
No, but
This is
wherever the T0 will occur, it is this, whether elastic or inelastic, because it follows from the Lehmann ellipse derivation. So you have to look at the T channel, proton, and then K bar is coming. So that mass is order of mass square is order of 1 over R square. Okay. So two ways of looking at it. Oh, well, this is an academic exercise, okay? Maybe totally useless, but then also you find that near forward direction, how you see this is rather weakly bound, okay? And that is still weaker. Okay, now I will just end in a few minutes.
So you got a cube instead of.
Yeah, because you see, imagine that F inelastic mod square is bounded by imaginary part of forward scattering amplitude, right? So this is obviously has to be weaker. So you can see through this, okay? You can see through this, but at least I cannot improve on this. Okay, so I'll basically end after this. See, actually, okay, let me give you 2 minutes summary of previous work. In 1969 or 70, Russians, Logunov and others, they're actually studying this kind of thing. But I'm surprised, Andre Martin's paper probably was published, but those days there are no archive or anything. So they don't quote actually Andre Martin's paper. That is okay. But what is important is they actually do not know where this cut begins. Okay. So they assume that there is an ellipse. Okay. So this is, it is given in some Marseille talk, high energy physics in some CERN conference. And so I got that. So but then this one, you see, I think Feynman actually proposed in 1969 that inclusive processes, that is the time inclusive was introduced into high energy physics. A plus B going to C plus X. Okay. So simplest example is deep elastic scattering. EP going to E prime plus X. and then of course the Feynman scaling and so on. But then he did it for hadronic processes, and there he actually, very intuitive argument, he showed that these cross sections must scale, the differential inclusive cross section. Not only that, this is quite important. Mueller, I think a year or so later, he actually proved so-called generalized optical theorem. Then A plus B going to C plus X, okay? You square it, sum over X. This is actually absorptive part, crudely speaking, of 3 to 3 processes, generalized optical theorem, okay? So that is actually useful. So here, you see, the invariant variables, because this is not fixed, this is an inclusive process. So T, momentum transfer square, and of course the center mass energy square, and mx square, okay? That is the missing mass square, right? So, so now in my case, you see, so I don't have to, in this kind of approach, I don't have to say what particle it is. It is just one particle or collection of particles, because that is X, okay? So the only energy momentum is to be conserved. So you see, this is bounded like this. But the differential cross section for inclusive processes, sum over all X, you see, then this appears, the average multiplicity of particle C, because you have to sum over all this. Then, so now the problem comes down to bounding this. So many years ago, okay, when I was young, so we wrote a paper in 1975. Of course, it has some little bit of extra assumptions in it. It is not first principle derivation. We actually bounded this average multiplicity. Forget about that, because the experimentalists actually measured these things at some. Okay, so you can actually find, and the advantage of this, you see, this cross section is much bigger than A plus B going to C plus D, because whatever is copiously produced is not observed. Okay, that cross section will be definitely higher. Okay, so this is my selling point. Okay, okay, I think I have told you everything. So. It's already 45. Okay, you can ask about analyticity theory of the non-compact theory. So that actually has been done. We can prove Gauss-Lehmann Dyson theorem, and then all this, whatever is there, it's a little bit painstaking, but you can do it. Because now the basis functions are Gegenbaur polynomials, so you have to a little bit worry about that. So this is for the 5-dimensional theory, as I told you, that I have derived. So, okay. So it is, you see, the total cross section is even worse. Okay, doesn't matter. The bound is. Okay, so I think I'll stop here, because we had a lot of discussions, and if you want to ask more questions, it is fine. But
Let's thank the speaker.
I'm very happy. Subrat is so much interested in. Yes.
Questions?
Next time you go to Sand, you fish out Atlas or. No, I'm not joking. See, I have been talking to these people, as I told you, except the COVID period. Wherever I go, I try to fish out. And
when I go there, my cross section with them is close to zero.
No, but you have to make you have to make an effort to know. But you see, it is quite interesting that there are these dedicated groups. Look, I mean, this is a laughing stuff, okay? But like, take one discovery of supersymmetry. There is a guy next door to my office in CMS, so every day I ask him, every day, is there any experimental evidence for Susi? So he's very annoyed. He's a young guy. He's very annoyed with me. You talk to people in sound. So you see, there are, I don't know, 32 models of supersymmetric model, and everybody has his own spectrum. Okay, everybody has his own Lagrangian, everything. When they are calculating cross sections, they are even calculating cross sections for FCC. Okay, so it is okay. So if me, okay, I'm making fun. I'm having fun. No, really. Look, I'm a retired person. Okay, so I'm having fun. And very fact that some people actually there, okay, they are willing to talk to me, I'm flattered. So the bottom line is this: if a dog can walk with 2 legs, it's already an achievement. The question is how well the dog walks. That's a different proposition. So I'm very happy. Yes, any question?
So
Yes.
somehow the degeneracy of the states and so on didn't even end. I mean, you have, I mean, because you would have, if you had many states, then it would just multiply by some.
Yeah, that is, you see, as I told you, that to get this kind of thing, what matters is the lowest threshold in the T channel, 2 particle threshold, okay, where the cut begins. That is phenomenologically, I mean, explaining. So, but then all this rigmarole of, over, what is this called, coincident region and so on, okay, that puts in a rigorous footing. But you can see that you cannot go beyond that point. So where analyticity in T channel is concerned. So that is all. And like other day I mentioned, before all these things happened, I think 1952, Heisenberg, he had some calculation, some intuition, and he said Hadron total cross section will grow as log a square. So what was the energy? A few hundred MeV cosmic ray energy, not even there any accelerator. So, and when he derived, actually today nobody will buy that bound. Okay, the constant, the prefactor is not fixed. They assume Mandelstam representation, which is never proved. Okay, all these things, but it sticks. And cross sections were all constant at that time. So his name stuck. Okay, so.
Feynman had some picture about the radius growing like log S.
No, that is Yang and Wu. So they assumed that proton actually becomes a disk at very high energy because of Lorentz contraction. And it is actually, you were in Stony Brook when he wrote, no, it's after you went. So disk, and then as energy increases, the radius of this grows as log of S. So you see log S square.
I mean, when a string kind of, you give a string a lot of energy, Susskind used to say also, right? It grows like, its size grows like log of the energy.
Yeah. So, but these are Yang and Wu, the first step.
So in some ways, this log of the energy size of in the transverse direction.
Yes.
Maybe it's a signature, universal signature.
Yes, intuitive way of looking at it. Like for example, when this Amartya Banerjee and all this company, they derive this result, okay? So, very nice result, okay? But those old guys knew the results of dual model, okay? So, yes. So, okay, so very good.
Yeah, I was just asking that, so usually these kind of things, one looks at missing energy and so on. Like looking at cross section is more effective.
Well, you see, question is you are after quantum numbers, okay? So there are 2 ways of identifying new quantum numbers. You see, it has to be in pairs because they are additive quantum numbers. So you have to determine at least one particle which has a quantum number, okay, which is not matching with initial. It has to be pair. But if you, actually I have no time to tell you several things. But you see, if you say one particle, look at one particle, and then you don't care Okay, there could be 3 particles. Okay, plus minus plus. Okay, there could be 5 particles like this. But cross section for this, okay, will be larger than the exclusive process. Okay, PP going to plus minus means KK plus minus. So this is kinematics, phase, all these considerations. Old timers used to do this. So this is the thing. So if it is not discovered, it is not discovered, okay? There is no stake. Unlike in case of supersymmetry, there is a stake that if don't see, then many of the things will be affected. But there is no stake in this. So that is the difference. But still good to try something.
Any more questions? If not, then let's thank the speaker once more.
Thank you very much. I'm so happy. I'm so happy. Subrata is asking.